Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and in the Masterstroke series where we are discussing one short chapter, today I am going to discuss about the chapter ray optics. So if you are preparing for KCET 2025 exam, then you should know that we have already started one short lecture, but due to PU2 exams it was halted. We didn't get time to record the lectures for Masterstroke. It is resumed. So after the resumption, this is the first chapter I'm going to discuss, ray optics. Okay, very important chapter. 4 questions, up to 4 questions comes from this chapter, and not super difficult, not super complicated chapter, because there is no combined combination concept from this chapter. Mostly standalone questions comes from this chapter, so not too many mixed questions, mixed concept questions can come from this chapter. So let's start with the chapter. First of all, obviously we want to look into the all important concept from this chapter, and then we will discuss all the concepts one by one. So list of important concepts: reflection and spherical mirrors. Obviously spherical mirrors do show reflection. Then we have refraction and Snell's law, another important concept. And then we have total internal reflection, we have lenses, very important, and we have optical instruments. Okay, these are the very important concepts. Out of that, optical instrument is not super duper important. Last 10 years only 1 or 2 questions came directly from optical instruments, but still if you are preparing right now, you cannot skip that. You have to study briefly about optical instrument as well. Okay, so let's start with the part reflection. So there are 2 laws of reflection. Obviously we know that the angle of reflection equals to the angle of incidence. Very simple, I equals to R. Next is the incident ray, the reflected ray, and the normal to the reflecting surface at the point of incidence lie on the same plane. Again, very simple. Okay, all the incident ray, reflected ray, they all lie on the same plane. Okay, so this is incident ray, this is reflected ray, this is normal, they all lie on the same plane. Even though my diagram is not super correct, but I hope this is the law that you are learning from a very small age. So first of all, incident angle equals to reflected angle, so I equals to R. Now sometimes they ask you what is the angle of deviation in this case. So angle of deviation means what? Angle of deviation means if there was no mirror, what is the original path of the ray? This is the original path, and by which angle it deviates. So that is called angle of deviation. So angle of deviation is nothing but 180 degree minus 2i. Okay, this is the formula, you should remember. This is angular deviation. Sometimes maybe easy question, if the question paper is easy, you might get this question. Sometimes if you don't study, then easy question sometimes appears to be difficult. Okay, now let's see. Spherical mirror is a part of a sphere with one side silver. So what is a spherical mirror? It's a part of a sphere. Sphere is obviously a 3-dimensional ball kind of shape. Part of it is silvered, and that means that side can reflect light. Okay, so there are the few examples you have seen. This kind of, this is a solar cooker, this is the most common example. This is the rear view mirror of your car. Okay, this is a solar cooker. This is a concave mirror, this is a convex mirror. Okay, now there are 2 types of mirror. One is convex mirror. Convex mirror is forms only virtual and diminished images. So convex mirror is when the curvature is outside. Okay, this is called convex. Okay, so light ray always travel from left to right. So this is the convex mirror. Okay, it is coming out. It always forms virtual and diminished images. Okay, and next is concave mirror. In case of concave mirror, forms real and virtual images both. So if there is a question which says that mirror which forms only virtual image, then that will be convex mirror. If there is a question based on that mirror which forms both concave and real and virtual images, then it is a concave mirror. Also you should remember that when it comes to the focal length, convex mirror is always positive focal length, and concave mirror always negative focal length. Okay, so we will discuss that again, don't worry about it, but just for your information. for object distances greater than f, it forms real images. So if the what is concave mirror, by the way? Concave mirror looks like this, okay? And for object distance, if this is focal length, any distance more than focal length, it forms real images. Any distance less than focal length, it forms virtual images. Okay, that is very, very clear. Now for object distances less than f, it forms virtual and enlarged images, which is very, very important. If you ever visited a dentist, okay, dentists usually use a mirror to see inside your teeth. Okay, that is because that mirror he is using, the dentist is using, that is a concave mirror which forms virtual but enlarged image when it is less than focal length. So basically the mirror is a very high focal length concave mirror. So when it put inside your mouth, okay, it forms a virtual but enlarged image, so that helps the dentist to identify if there is any cavity inside or anything broken inside, right? Now let's move on. Sign convention, very important. So sign convention, that's I said that anything on this side, negative side, so this is an x-axis basically, okay, and positive x-axis, this is the origin, this is the origin, this is the origin, okay. Any distance is measured on the right hand side is positive, any distance is measured on the left hand side is negative. Similarly, any distance is measured along the y-axis, positive y-axis is positive, anything measured in the negative y-axis is negative. Okay, so object heights are generally, if it is a real image, heights are generally negative, but sign does not important, sign is not important along the y-axis, sign is important along the x-axis. All the calculations by this object, when object is kept some distance, this is called object distance, right? So object distances are always negative, object distances are always negative. Now image distance based on the whether it's a mirror, whether it's a lens, whether it's a real image or virtual image, it can be positive, it can be negative, but object distances are always negative. For example, if you are considering a concave mirror and the image formed is real, then object distance is negative, image distance will also be negative. Now if the image formed on the other side behind the mirror, that is a virtual image, in case of virtual images, image distance is positive. For concave, for mirrors, for lenses it is opposite, okay. So be careful, don't confuse with that, but u will be given to you, you have to find the v's most of the cases. What else? Let's look into the mirror equation. So mirror equation is this, 1 by v plus 1 by u equals to 1 by f or 2 by r. Now mirror equation, we I prefer to write it like 1 by v plus 1 by u. Why? Because same thing, if you put this change the sign to negative, it becomes lens equation. That is why I like to write it 1 by v plus 1 by u. In your books maybe it is given as 1 by u plus 1 by v, no problem, but if you want to remember only one thing, then 1 by v plus 1 by u is easier to remember. Only plus and minus you need to change for mirror and lenses. Okay, this formula is valid for all situations, for all spherical mirrors, for all positions of the object. Okay, this is valid for all situations. You must use new Cartesian sign convention. The Cartesian sign convention I already explained. Anything along positive x-axis is positive, anything along negative y-axis is negative. You will start measure from the origin, which is the pole of the mirror, okay, or center of the mirror. What else? This is the magnification formula. Magnification is given by minus v by u, right? Now let's see one problem from KCET. Okay, this is a KCET problem. A point object is moving uniformly towards the pole of a concave mirror for focal length 25 centimeters. So concave mirror is given, focal length is 25 centimeter given, okay. Mirror focal length 25 centimeter along its axis as shown below. The speed of the object is 1 meter per second at t equals to 0. The distance of the object from the mirror is 50 centimeter. The average velocity of the image formed by the mirror between time t equals to 0 and t equals to 0.25 centimeter is. This is t, okay. This is t equals to 0.25 centimeter. Now let's solve it. So what is speed of the object? Speed of the object, speed we generally denote with the symbol u, but u and v are generally used here as object distance, image distance. So what I will do, I will use a symbol capital V for speed. Okay, generally capital V is not the symbol for speed, it is symbol for voltage, but to make you understand that capital V is the speed of the object. Speed of the object is given 1 meter per second. So 1 meter per second means 100 centimeter per second. Why I am doing opposite way? Because that is easier. All the distances for a lens or mirror is generally given in centimeters. That's why I have done the reverse conversion, not the other way around. Okay, so the speed of the object is 100 centimeter per second. Now after, from time t equals to 0 to time t equals to 0.25 second, we have to find what is the how much displacement happened. So displacement S equals to V into T. So the displacement is V into 0.25, so that is 100 into 0.25, that is 25 centimeter. This is the displacement. So the object started at 50 centimeter and it is moving towards the mirror, right? So after 0.25 second, the object will reach exactly at 20, this distance should be 25, right? This is the distance, 25 centimeter, this is the distance, this is the displacement of the object. So you have calculated the displacement of the object. So what is the new object distance? The new object distance is initial object distance minus the displacement. So initial object distance was 50, final object distance, the displacement is 25, so the final object distance is 25 centimeter. So basically the object is now at 25 centimeter, that is exactly at focus. So if the object is exactly at focus, where will be the image formed? So when we keep an object at focus for a concave mirror or convex lens, the image formed at infinity. So image is here is forming at infinity. So image which was initially here that is at 50 centimeters, suddenly after 0.25 second it reaches infinity. Okay, so what is the displacement of the image? Displacement of the image, okay, say SI, that is displacement of the image, is basically infinity minus 50. So obviously infinity minus 50 means infinity. So speed of the image is infinity divided by 0.25, that is equals to infinity. So speed of the object will be infinity. So answer C is correct, right? Now let's move on. This is a very interesting question, and because of the answer many students got it wrong, they answered it wrong. Okay, calculus is not required to solve this question. You can simply solve it by the understanding that how much distance it moved. If you get that, okay, distance moved by them is 25 centimeter, that means final distance is 25 centimeter, that means object is located exactly at focus. When the object is at focus, final image is at infinity. Final image is at infinity means speed should be infinity, right? Now if you are also want to reach infinity by cracking your KCET exam, then definitely you have to take our Abhyas KCET 2025 test series, where we are going to give you total 35 tests. Out of that 4 tests are already available in our website. The link for Abhyas KCET test series is given in the link below. Don't forget to register yourself before the time runs out, before you are out of option, right? And the price for entire test series is 1498. 1499 is including your KCET PU board exam, but PU test series is already almost over now. Main exam, maths and physics exams are over, chemistry exams about to happen, right? So all the papers are happened, so you don't need to buy PU2 test series, you just buy 1498 for the Abhyas test series, and you will get a detailed video solution for all the question papers that we are going to discuss as usual. Also you will get all the chapter one shot revision videos, chapter insight for last 5-year KCET papers, also live doubt sessions. So we will be coming live, all the teachers will come live and discuss the doubts with you in live session. So don't miss out on that. Okay, whatever doubts you have, you can ask us in the live session, and once you join our program, you will be given a WhatsApp channel link dedicated for Abhyas KCET test series. So once you join the Abhyas KCET test series, through that link you will be able to access the exclusive content available only for you, right? Also, it is only available through the app Novo Parent app, and you don't install Novo Parent app straight away. First of all, you have to register yourself in the website, through then you can go to the Novo Parent app. Right, now laws of reflection. Let's look into laws of reflection. So the incident ray, the refracted ray, and the normal on the interface of the point of the incidence, all lie in the same plane. First law, in case of refraction, it is obviously reversed. Why? Because second law is very, very important, which is also called Snell's law. Snell is not the snail which walks very slowly. It is a person's name. Okay, so the ratio of sine of the angle of incidence to the sine of the angle of refraction is constant. Remember that the angles of incident and refraction are the angles that the incident and the refracted ray make with the normal respectively. So incident angle and refracted angle, they are always measured from the normal, and if the incident is directly normal, then Snell's law is not valid. There was a question in PU board that when Snell's law is not valid. So if the ray is falling coming directly along the normal, then the Snell's law is not valid, because in that case I is 0, R is also 0. So sine of I by sine of R does not make sense. It is an infinity value. So you cannot apply Snell's law when the for normal incidence. For any other incidence, angles are always measured with respect to the normal, right? Now formula says that sine I by sine R is equal to n21. This n21 quantity is called the refractive index of the medium. Refractive index of the second medium. Second medium means the final destination where the light is entering. That medium's refractive index, n21. So it is refractive index of the second medium with respect to first medium. If the first medium is vacuum, then we call it as absolute refractive index. Okay, so refractive index, obviously we know that. Now here n21 is called the refractive index of the second medium with respect to the first medium, and if n21 is greater than 1, that is R is less than I, that is refracted ray bent towards the normal, in such case medium 2 is said to be optically denser than medium 1. So if the light ray falling on a medium after incident, okay, the ray bent towards the normal, that is R is less than that of I, then definitely the refractive index of n21 is greater than 1, then we say this is a optically denser medium. This is an optically denser medium. If it happens opposite way, then it is called optically rarer medium. On the other hand, if m21 is less than 1, that is R greater than I, the refracted ray bends away from the normal. This is the case when incident ray is denser medium, refers to as rarer medium. Now let's continue with refractive index. Refractive index is dependent on the wavelength of the light. Okay, refractive index is inversely proportional to the wavelength of the light. Very, very important. So if you are asked that for which ray refractive index will be more, red or violet, then you can answer that refractive index for violet will be higher than that of the red. Why? Because red is higher in wavelength, that means refractive index should be smaller. Violet is smaller in wavelength, that means refractive index will be higher for that. Okay, so based on the color, refractive index varies, and it varies inversely with the wavelength. What else? Also, refractive index is dependent on the speed of light on the medium. Very important how it changes. The absolute refractive index, that is refractive index. What is the meaning of absolute refractive index? So if you make the first medium from where the light is coming, suppose I want to measure the refractive index of, say, water. Okay, so if I make the first medium as air or free space, that is vacuum, then the refractive index of this is called absolute refractive index. Okay, so absolute refractive index is when the first medium is air or vacuum. Okay, generally air has a very small refractive index, 1.001 or 1.002, but for all practical purposes we say that refractive index of air is also 1, refractive index of free space is also 1. So if there is nothing, refractive index is always 1. Absolute refractive index cannot go below 1. Okay, absolute refractive index cannot go below 1. Yes, relative refractive index can go below 1, but absolute refractive index cannot go below 1. Why? Let's see the definition. So refractive index is, absolute refractive index is defined by speed of light in vacuum or air, C is both cases, right, divided by V. Divided by V, V is the speed of light in that particular medium. Okay, so C is the speed of light in vacuum or air, and what is the value? Value is 3 into 10 to the power of 8 meter per second. V is speed of light in medium. Also note that speed of light in air or speed of light in vacuum is the maximum possible value, right? So that based on that, Einstein gave his beautiful theory of relativity. Okay, I'm not going to talk about that anyway in this class, but you should know that speed of light is the maximum possible speed, right? So it is always it can be lowest possible value of absolute refractive index is 1. That is for air and space, where speed of light is equals to C. Other than that, for any other medium, speed of light is always less than C, and that is why absolute refractive index cannot go below 1. Very important concept. Relative refractive index can go below 1. What is relative refractive index? Relative refractive index is when we are measuring the refractive index of one medium with respect to another medium. For example, I want to measure the refractive index of water with respect to glass. Now glass absolute refractive index is higher than that of the absolute refractive index of water. So in that case you will find that refractive index will be refractive index of water with respect to glass will be less than 1. Okay, so there are possibilities that because speed of light varies from object to object. For another example, refractive index of air with respect to say glass. So refractive index of air with respect to glass will definitely be less than 1. So relative refractive index can be less than 1, but absolute refractive index cannot be less than 1. Okay, now, let's see one problem. An equiconvex lens made of glass of refractive index 3/2 has a focal length f in air. Okay, it is completely immersed in water of refractive index 4/3. The percentage change in the focal length is. So this is a question based on the lens maker's formula. So 1/f equals to n/1 minus 1 into 2/r. For all purposes you can take r1 minus 1/r1 minus 1/r2 to be 2/r. Okay, fine. Now first case, refractive index is 3/2 with respect to air. Okay, so first case it is given in air, that means absolute refractive index, right? So let us put that value. So 1/f is given obviously, and refractive index is given 3/2 minus 1 into 2/r. So you will get this as 1/2 into 2/r, that is 1/r. This is the refractive index. So focal length is equals to radius of curvature. This is case number 1. Okay, now second case is then you are immersing it into the water. So when you immerse it into the water, let's say the focal length is f dash. So what is f dash? F dash will be equals to refractive index, absolute refractive index of the glass, that is the medium of the lens, divided by refractive index of the surrounding medium. You have to remember that. Okay, with respect to, as saying that with respect to whatever is respect to, that should be in the division. -1 into 2 by r. Okay, so now 9 by 8 minus 1 2 by r. Okay, or you should be able to solve this kind of problems. Now it will be 1 by 8, okay, into 2 by r, that is 1 by 4r. So the focal length is now f dash equals to 4r. Okay, right? So focal length is 4r. So what is the change? Very careful that they have asked you percentage change, not the new focal length. So what is the change? Delta f. Delta f is f dash minus f, that is 4r minus r, that is equals to 3r. So percentage change, delta f by f. Okay, I am doing in detail so that you don't miss out on anything. So r cancels into 100%, that is 300%. So change in focal length is 300% increase. Okay, because the final focal length is more than that of the initial focal length, so 300% increase in focal length. Okay, clear? If you have any doubt in any of the concepts, any of the questions that I am solving, please don't forget to mention in the main comment below. Don't leave the chat, don't leave the comment in the live chat session, because otherwise I will not get that chat. See later on. Okay, so mention in the main comment down below. Okay, now let's see. Next is total internal reflection. So when light travels from optically denser medium to a rarer medium at the interface for a certain angle of incidence, the refracted ray of light passes exactly between the planes separating the two medium. Right? So hence the angle of refraction in this case is 90 degrees. This angle is called critical angle. So basically, just briefly explain me that when the light is traveling from a denser medium, for say water, to a rarer medium, say air. Okay, what happens? We know that when light traveling from denser to rarer medium, it bends away from the normal. Okay, so what happens is that the ray, as usual, bends away from the normal. Okay, now if you keep on increasing the angle of incidence, at certain angle, suppose you have increased this was suppose I. Now you increase the angle of incidence to certain more angle. Okay, then what will happen? Now you are increasing the angle this side, so the angle on the other side has to increase, right? So what will happen? This will also increase and it will pass directly between the medium separating the two media. This is called a critical angle, theta c, IC, whatever you call it, this is called critical angle. In this case, the angle of refraction is 90 degrees. Now what will happen if you keep on increasing the angle more? If you keep on increasing the angle more, then instead of going to the first medium, entire light will come back into the water medium. Instead of going it to the air medium, entire light will come back to the water medium. So what happens is basically this is called total internal reflection. Okay, when the angle of incidence is greater than the critical angle, the incident light, instead of refracting to the second medium, reflects back to the first medium. Okay, this is called total internal reflection. Now there is one important relationship, is that this is the formula for refractive index of this medium. Refractive index of 1 with respect to 2. This is 1, this is 2. Okay, so refractive index of the medium, generally second medium is air or vacuum, first medium is generally water or glass. So that is why we say this is the refractive index. In case it is happening, say, from glass to water, it can happen from glass to water as well. So in that case, it will be refractive index of the first medium, that is the origin medium, divided by refractive index of the ending medium, final medium, that is given by N21. Okay, this is the same thing. Okay, this phenomena is called total internal reflection. Now there are some application in case of prisms. Total internal reflections are used. Okay, this is a case where it is reflected. So if you see that this is the original size, now after that the image is reflected by 90 degrees in this case. So final image, initial image was like this, final image is like this. So it is transferred by an angle of 45 degrees. Suppose you want to watch something but the angle is not perfect. So this kind of prisms are used. These are called total internal reflections. Reflection prism, as you can see, it is designed such a way that the both angles are 45 degrees. In this case also both angles are 45 degrees. Okay, in this case also these angles are 45 degrees. Okay, and it is designed such a way that an object coming like this, they will reflect from this surface and they will come back. So it is happening from the hypotenuse side. If you see, all the sides are different. Now if the light ray is entering through hypotenuse side, it is basically getting inverted. Okay, but it is happening, everything is happening on the same side of the prism. So object was in this side, image is also forming in this side. So here is the camera, suppose the projector, here is the observer. So if it is happening on the same side, then we use this kind of prism. But most cases you want to show it to the other side of the spectator. Other side someone is watching, you are projecting from this side, someone is watching from that side. In that case what happens, you have to put the light like this, and it should enter from one of the curved side, and then it should reflect back, and again it is getting inverted by 180 degrees. Okay, these two cases 180 degrees, this case is 90 degree. Okay, so these are the total internal reflecting prism. Now optical fiber also utilizes total internal reflection. Generally there is a high refractive index core present inside an optical fiber with a very low refractive index outer core, so that the ray of light traveling here can go totally reflected through the medium, okay, without getting refracted back. Now the medium which is taking the light generally absorbs some portion of light, but that is very, very less compared if you have send the signal directly. Okay, signal attenuation is not happening, and that is why we use optical fibers for data connection, for transmitting data, transmitting light, transmitting signals. Everything happens through optical fibers because they can carry signal for a very long distance without any need for amplification. For example, if you send data, okay, through normal copper cable, after every say 1 kilometer or 500 meter you have to use a signal booster. Okay, for optical fiber you can send it up to 10 kilometers, okay, without using any signal boosters. 10 to I think based on the quality of the optical fiber, you can send data up to 100 kilometer without requiring any signal booster. Okay, for example, one of the longest data cable is there in the Atlantic Ocean, transatlantic data cable. Okay, that is through which the data is transferred from US to Europe, and through then it comes to India as well, Asia Pacific. So that is the reason Pacific cable is also there, but it is not completed, I think. So there is a plan that there will be direct connection between USA and India. That plan is going on. Maybe it will be fruitful in future. So there are a lot of undersea cables where we use optical fibers, very high quality optical fibers, so that through the continent it can travel without requiring much booster. Booster is there in between. They know where the boosters are, so they can service it, but boosters are located somewhere safe, somewhere accessible location where the most of the cable are undersea, where there is no boosters, right? You cannot occasionally you cannot go down the sea and change the cables if required, right? But you can just change if the booster is making any trouble, you can just change the booster. So that is possible. Now let's move on. refraction of spherical surface. Here is a spherical surface, so light ray is traveling through a sphere, and the relation is very simple, N2 by V. So you have to remember this is the same similar equation that of the lens equation. Only thing is that N2 is the second medium, V is also in the same medium. So N2 by V minus N1 by U equals to final refractive index minus initial refractive index divided by the radius of curvature of the spherical surface. Now here sign conventions will apply as usual, and mostly I have not seen any numerical questions coming from this formula in your KCET last 10 years, but maybe this is the year where they will ask, because there is a very common formula and it is included in your syllabus. So they might say, okay, we have not asked, but this year we will ask. Now let's see the lens maker's formula, which I was discussing formula problem previously. So 1 by F equals to N21 minus 1 by R1 minus 1 by R2, and for all practical purposes wherever you are using this formula, okay, you can write this as 2 by R. Okay, convex lens 2 by R, concave lens there will be a negative sign outside. That is the only difference. This is for convex lens, you can easily use this. For concave lens you have to use a negative sign. That's it. Other than that, you can use this formula by closing your eyes. Okay, generally R1 and R2 are same, and if this is positive, this is negative, like that, this one is R1, this is positive, this is R2, this is negative. That is why you have to put a negative sign over here, and then eventually you can use this. Now let's move on. Lens equation, obviously this is mirror equation, this is magnification, and this is power of the lens. This is power. Okay, power of a lens is given by 1 by F. Now here you have to remember that this is lens equation. We all know that magnification V by U also we all know that, but here in case of power you have to remember that focal length is in meters. In this case focal length must be expressed in meters. Okay, in case focal length is given in centimeters, then you should remember in your head that power will be 100 by F if F is in centimeter. Now you should remember that most cases whenever you are solving problems based on lenses, focal length is most commonly given in centimeters. Okay, so you have to be careful. This formula is only when focal length is given in meters. Okay, and the SI unit of power is diopter. One diopter is 1 meter inverse. Okay, combination of lenses. So if you have two lenses combined, one after another, two thin lenses, obviously even more than two thin lenses also, this formula is valid. As long as they are thin lenses, the combined focal length is given by 1 by F1 plus 1 by F2. Okay, for two lenses you can use the knowledge that this is similar to that of the the resistances in parallel, so you can use this formula as well. And in case of powers, power simply gets added. Okay, P1 plus P2 plus P3, because 1 by F is P, 1 by F1 is P1, 1 by F2 is P2. But again, powers, for calculating powers, F should be expressed in meters. Okay, now let's move on. Refraction through a prism. This is another important part. Okay, angle of incidence, angle of refraction, and refractive index. Okay, so this is the angle of incidence for a refraction through a prism. So prism 1, I know those who have just coming out of PU board, they know that. Those who have passed last year, they should also remember it, by the way. So this is the diagram. Okay, so this is the angle of prism A, this is the angle of incident I, this is the angle of refraction E, and in case of this is the delta. In case of minimum deviation, obviously I becomes equals to E, and that is why this is the formula. This is for minimum deviation. If minimum deviation is given, you can use this formula to solve any numericals, okay? And the refractive index is given by sine A plus delta m by 2 divided by sine A by 2. Now optical instrument, this is the last concept. So optical instrument, there are two optical instrument. One is obviously the microscope. For a compound microscope, the formula is L by FO plus D by FE. What is L? L is length of the microscope. That is the distance between objective and eyepiece, okay? That is the distance between objective and eyepiece. D is the distance of minimum vision, 25 centimeter, okay? For normal person it is about 25 centimeter. FO is focal length of objective lens, and FE is the eyepiece, focal length of eyepiece, okay? Got it? So this is how you can remember it. That, as I said, this related questions never came in KCET. Only once it came, but you can remember these formulas. Maybe they will ask some question based on that. And telescope focal length, telescope is easy. Objective by eyepiece, you have to remember objective by eyepiece is the magnification. Whenever you are observing a small object or a very distant object which is apparently very small in size, the magnification is very, very important, right? So if you want to see a small object, it should be appear somewhat big so that you can see it, right? All the distant stars we are seeing a very big images of them. How we are getting that? Because telescopes are observing the distant objects. Similarly, the small cell structure, mitochondria, etc., how we are observing them? Because there is a microscope, okay? For simple microscope, this is only for simple microscope. Simple microscope means the Sherlock Holmes detective microscope, that is the only single convex lens. This is the focal length, this is the simple microscope. Focal magnification for also it is V by U, if you remember. Other than that, there is no other concept left in this chapter. If you have any doubts, don't forget to post that in the comment below. Also, if you are watching this channel for the first time, don't forget to subscribe to our channel. And one more point I missed. Refractive telescopes has zero chromatic aberration. So there are two types of telescopes. One is reflecting telescope, one is refracting telescope, okay? Not refracting, it will be reflecting. Okay, refractive telescopes are like which uses lenses. Refractive are lenses, combination of lenses. Reflective is where we use mirrors. Okay, concave mirror, convex mirror, they are called reflecting telescopes. Now, as I was saying, if you have not yet subscribed to our channel, don't forget to subscribe to our channel. All the important updates, all the important concepts will be going to be discussed in our channel, so don't miss out on that. I'll be back with wave optics chapter very soon. Till then, bye.